right. Thanks, everyone. Yeah, thanks, Max, for a really great talk. I'm excited to be here this morning to give a little bit of a perspective on HTAP, starting from the analytics side, based on things that we're seeing at Databricks. Basically, I think this is a really exciting time to be working on data systems, and the HTAP systems, like what Max talked about, what he's doing with TiDB, are an example of how people are innovating in this space. So what's kind of changing in the world of data? So there are actually a lot of exciting things going on. The first one is that enterprises in all industries are actually starting to collect very large data sets. It's very common now to have petabytes of data, not only at web companies, but even at sort of your traditional enterprise that you've heard about, your retailer, industrial companies, and so on. The second thing is that many of these enterprises are also starting to adopt real-time applications, which they can do as they collect this data from automated systems. And also many of them are starting to adopt machine learning. So it's a really good time for kind of new data systems at all levels of the stack. So I'll give you the perspective on this that we're seeing at Databricks. We're an analytics-focused company, but of course people connect Databricks to a lot of online systems as well. So if you're not familiar with us, we're a Bay Area startup, a cloud-based data and AI platform. We have over 7,000 customers worldwide, and people use us to run some pretty large-scale workloads. So we run over 15 million VMs per day to run data and AI workloads for our customers. And we process exabytes of data per day. We also have exabytes of data under management in the platform as a whole. And the idea is to build an end-to-end platform for data and AI as a service, so a company can just stand this up and have a complete stack that works well together. So it goes all the way from kind of simple SQL data warehousing to ETL, streaming, data science, and machine learning. These are some example use cases. We have, as I said, companies in many kinds of industries using us, and these are some of the ones from what you wouldn't think of maybe necessarily as tech companies doing streaming or doing machine learning, but actually these are very big use cases in there. So industrial companies like Shell are using us to optimize their production using petabytes of data. HSBC is an example of a bank that has over 170 petabytes of data worldwide, and they built a lakehouse system using Databricks to query that and combine that in what used to be 14 different databases. And then Regeneron's a biotech company that is using large-scale data sets to design new therapies. And this plot here is showing sort of the growth of our platform, of the compute workloads we run over time. You can see they're still growing quickly. And of course, managing this kind of platform, it's all a cloud service, is quite challenging. So I'm going to talk about two things today. First of all, I'll talk about how these analytics use cases that we work on are becoming more and more real-time, and I'll talk about two trends in there, which are lakehouse systems that are a little bit like HTAP. They're kind of this hybrid system that reduces the time to get sort of value from data, and also about the rise of streaming, which is something we've been seeing a lot of recently. And then I'll also talk about how in Databricks itself, to run the control plane that runs these 15 million plus VMs, we are starting to use TiDB and HTAP-like systems ourselves to deliver our own service. Okay. So I'll start with the first one. Why is the analytics world moving more towards real time? And that has to do with the challenges that data users have in most enterprises. So it turns out if you ask most people who have to use data in their company, what's the problem with data? They're not going to say, I need a faster engine, or I need a more scalable engine, or I need this function in SQL, or something like that. The top problems they have are often to do with just data quality. My data is wrong. I can't do anything with it. Or with timeliness. I don't have the most recent data. I can't build this application because it can't see what's happening in real time. So this is an example of a survey from Fivetran, which is heavily used by data analysts. They just surveyed data analysts and asked them about challenges. And the top challenge 60% of the data analysts reported data quality as a top challenge. But another surprising thing was that 86% said they had to use stale data that was days or weeks old, and 41% said they had to use data that was more than 2 months old. So of course you can't do great analysis in your company or build a really powerful real-time application like we saw if you're working with very old data. And of course many of them also had issues with reliability and other things like that. So getting high quality, timely data is quite hard when you have a lot of systems in a company with a complex deployment. But one thing I want to point out is that it's also partly due to the design of kind of legacy data systems that people are deploying. So let's go on a short kind of history of analytical database systems and kind of figure out why we got to this spot and why it's so hard to do this. So back in the 1980s, this is when people first started building dedicated SQL systems for analytics, which were called data warehouses. And the vision in there was really nice and simple. It was you have all these operational databases, your transactional ones, and as events happen into those, just load them directly into this system that's optimized for SQL on historical data. That was the data warehouse. So you have extract, transform, and load, ETL, and then you load them into this system that's optimized for it, and you get all the powerful features of SQL, transactions, indexes, schemas, and so on, except now it can work on your historical data. And that worked great, and in these systems you could get data into them in seconds or in minutes, and then run these analytical applications. Now, unfortunately, as data volume scaled up and as applications became more diverse, these systems started to hit some problems. So for example, they couldn't work well with unstructured or semi-structured data like time series and logs because they were all designed around tables of records. They also had a high cost. They weren't designed to be cost efficient for really large data sets, and so that became a problem. And also they couldn't support workloads other than SQL, like data science and machine learning. So because of this, most companies started deploying a second kind of system called a data lake, which is basically a system that just stores files very cost efficiently at scale. And these are actually the most widely used storage systems in terms of volume in the world. Like more than 90% of data in a typical company will be in one of these systems. These are things like Amazon S3 or HDFS for on-premise, or basically these kind of file systems. And on these, you have a different design. They have a much lower level interface. It's just a file system. And people will usually store data on it using these open file formats that can represent things like tables. But you can put anything you want in them. You can also put images, videos, whatever you want. And because people have adopted these open file formats, you also have this great ecosystem on top of open source engines that can read that data and do things with it. Like Apache Spark, for example, came out of this world, but many other things. Apache Flink, Pandas, TensorFlow, PyTorch, all these things can work with the data and the data lake. And then in your enterprise, these are the bottom layer where most of the data lands, and then you select subsets of it that you load into a data warehouse, and then maybe you process it further, and then you can do the high-performance analytical applications on that. So of course, with this kind of stack, with two systems, you end up with some challenges. It's nice that it is cheap to store all the data, and then you select the pieces you want the high-performance SQL on, but it's also complex. Reliability of your data suffers because it has to pass through all these stages. It has to first get in the data lake, then be processed and loaded into the warehouse, then maybe be transformed further. And each of these steps can go wrong and can lead to corrupted data or missing data downstream. And also your timeliness suffers because there are so many steps before the data gets in the warehouse where many of the end users like analysts can query it. They're not allowed to go back to the raw files and query that, and so they can't see the latest data in there. So this is where lakehouse systems come in. This is kind of the architecture that we've been pioneering and pushing, which is implementing the data warehouse functionality like high performance indexes, transactions, versioning, and so on, directly on data in open formats in low-cost data lake storage. And if you can get this to work, the architecture would look a little bit like this. You would get all the data landing in these low-cost storage systems at the bottom in open formats, and then you could query them with SQL and get really high performance through that interface, or you could query them directly in systems that can read the raw files like TensorFlow, Pandas, things like that, to do data science and machine learning. So of course, the question with this is, can you actually get state-of-the-art performance and management features with this hybrid design? It's a lot like the HTAP question, right? Can you actually be good at transaction processing and at analytics with this hybrid system or not? So this is actually happening, and I'll tell you a little bit of what we've seen, and we're not the only ones going in this direction, actually, to make this actually work. So I'll talk about two key technologies that are enabling this lakehouse design. Metadata layers on data lakes that add the transactional and management features, and then query engine designs that can work well in this domain and can work well both with kind of unstructured data just as it lands in, and with techniques that improve performance significantly for your relational tables. So let me start with this one. So these metadata layers are probably the most significant trend kind of in the data lake world today. There's systems like Delta Lake, Apache Iceberg, Hive Acid, and they've become extremely popular in the past few years. And the idea there is simple. You've got your data lake, which is just a file system at the bottom, but you have this layer on top that keeps track of which files are part of a particular table version or dataset version. It doesn't have to be tables. And this can operate transactionally, and basically this is where you start to get transactional features. So when you have an application that wants to read a table, instead of just going to the file system and doing a list and seeing a million files, it can talk to this layer and ask, hey, which files are part of the latest version, and this layer can return something back. And this is a very simple kind of client library you can plug into any system. And then you can just read these files with high performance from the underlying storage, like say from Amazon S3, and run your application. So this is a very simple design, but it solves a lot of issues that data lakes have and allows you to get this kind of hybrid system with a lot of the capabilities of a traditional data warehouse. So just as a simple example, I'll show how you can do transaction processing all these, and I'll start by explaining the problem with trying to do transactions on a data lake, right? So if you just have a normal data lake, which is just a file system, and you're trying to do transactions, the problem is you don't have atomicity. So imagine we have a table, it's stored as a bunch of files, and now some transactions come in that want to update some of the data in there. For example, delete all the records about customer ID 17. Well, with a file system, you can't make this happen all at once. You have to go file by file, maybe in parallel, and update them to do these operations. So for example, for the first file, you might rewrite it to file 1b.parquet, and then delete the original file. And maybe there's also data about this customer in the last file, so you want to rewrite that and then delete this one. Now, at any point in this process, things can go wrong if someone tries to read the table because they'll see something inconsistent. And same thing if your query that's trying to delete this data crashes, then you'll just leave the table in a corrupted state. So that's basically the problem here. I'll explain how we solve this in Delta Lake, which is an open source metadata layer that we built at Databricks. It's hosted at the Linux Foundation now. And other systems work in a similar way. So the idea is really straightforward. In addition to the data files for your table, we have this transaction log. And actually in Delta Lake, we store this in the file system as well, in Amazon S3 or HDFS or whatever. So as long as Amazon S3 is up, your table is readable. You don't need any other system to be running necessarily, which is really cool because S3 has super high availability and performance and all that nice stuff. So what we have is we have a structure in there that's basically a write-ahead log that tells us which files are part of each table version. It's actually smarter than this. This is making it seem like we have all the data in each entry, but actually it's an incremental one that just stores deltas. When you want to do a transaction, you can go ahead and update the files, but because the log hasn't been updated, no one's going to read those incomplete updates until you're ready to commit. And then when you commit it, you can just add a new entry atomically to the log. There's different ways of doing this. And now clients see the new version. So a very simple idea. We have a paper about it if you want to read, but it unlocks many powerful capabilities. And so using this as the basis, we've been able to build a lot of the things that in the past required a separate storage system to manage your data. So for example, one thing you can do is you can treat Delta Lake tables as streams, as something like a Kafka topic. So you can have streaming jobs that just listen to the changes and make something happen. And likewise, you can have streaming insertions into them with exactly one semantics using transactions. So a lot of people are using it to replace the need for this kind of message bus. You can do time travel to see old versions. If you mess up something in your data, you can just go and read the old one from the log. You can do zero-copy cloning for development. You can take a table and create another table that points to the same files at a specific version without having to copy them. And you can even do cross-organization sharing. We have this open protocol where you can serve part of your table to another organization securely, and they read it directly from S3. You don't need to stream all that data through a bunch of nodes that are really expensive. So this has quickly become the most widely used storage format among our customers, and I think also among a large fraction of just open source Spark users in the world. It came out in 2018, and since then it's grown to 70% of our workload across the platform, like in terms of writes. This is very surprising because usually storage systems are some of the things that people are most scared of changing, and this was this new open source project, so it's very scary to adopt, but the benefits kind of outweigh it, and now it's become this extremely battle-tested thing. And it's also widely supported in the industry with connectors from lots of leading tools. So that's the metadata layer, and that's kind of the future of data lakes. I think pretty much everyone starting one today is using one of these transactional layers. And then the second piece of the puzzle is the query engines, and I'm not going to go into a lot of the details there, but basically we and others have been able to show that you can get state-of-the-art SQL performance on top of this data in data lake systems in open formats. We have an engine called Photon that's doing this, that actually set the TPCDS data warehouse benchmark record last year. It's also quite a bit faster on comparable hardware than some of these like leading cloud data warehouses that I'm not going to name here, but they're sort of the popular ones you can imagine. We have a whole bunch of techniques in there to make it work. Like once you have these Delta tables with transactional semantics, you can do things like maintain indexes, maintain caches, maintain statistics about them in a transactional fashion. That's always correct. And that enables us to get really good performance on these tables. So basically, you don't have to leave the data lake and copy data somewhere else to get really good performance. And then the final thing I'll mention that Lakehouse works really well with is streaming. I mentioned it a little bit before. But streaming is also a very large trend that we're seeing. We were surprised to see so much adoption of it in the enterprises outside of the traditional tech companies. So as enterprises collect more data in real time, and as they land it in systems like the Lakehouse where you can actually query it and manage it the moment it lands in there without having to wait to copy it into somewhere else, they also want to use it in real time. So today on our platform, streaming is actually more than 1/6 of the job workload. This is all the automated workloads on the platform. And there are quite a few use cases you can imagine, just incremental ETL, just getting the new data very quickly, but also things like fraud detection, monitoring, and so on. This plot here shows the number of streaming jobs registered on the platform. You can see it's millions and is going really quickly. Here are some examples of companies that are using streaming that are like publicly referenceable companies on the platform, and there are quite a few use cases, and overall it's grown by a factor of 9 in the past 3 years. So what matters for streaming adoption? So usually streaming is considered very complicated because you have to have a specialized engine for it, maybe something like Apache Flink, and then you have to have a team that operates it, that's experts in that technology. And it's pretty heavyweight to build a streaming team and a streaming application. So we took a different bet. We wanted to go with how to make this usable by the widest range of organizations that don't have to invest so much in it. And so we think that enterprises need ease of adoption for streaming and also ease of operation. You shouldn't have to get a PhD in how to run the streaming system. It should be sort of foolproof. So we target both of these with Apache Spark structured streaming, which is the engine we are contributing to. That's open source. So how does it work? So for ease of adoption, if you're not familiar with it, basically structured streaming is part of Spark SQL, the relational processing layer in Spark, and it's basically the same API. For many types of queries, you can take a query and say, instead of doing this in batch, run it incrementally as a stream. So when data changes upstream, it just computes the differences. And the API is just you change the input and output of your computation. So I have an example batch computation there. If you just change a couple of words in it from read to read stream, you now get a streaming computation. And then in terms of operation, it builds on the Spark engine, and we prioritized fault recovery and making it very easy to shut down, update the application, and also to scale it to large amounts of data. So because Spark did all those things, and this builds on the same engine, you get a lot of these features kind of for free from it. So you get fault recovery, straggler mitigation. If a node is slow, we can just skip it and do the work somewhere else. Elasticity, very easy restart. You can just shut down the application anytime and restart it, and also scalability. So this is an area we're investing heavily in the open source project. We have this effort called Project Lightspeed, and we've hired a really great team of streaming sort of pioneers to work on this. And so some of the things that we're working on are lowering the latency. We've been able to lower the latency of Spark streaming by more than a factor of 10 already for applications that need that. Improving just the functionality, the richness of APIs available, and also making it even easier to observe. So we're very excited to invest in this and see hopefully even faster growth of it. Okay, so that's a little bit of what's happening in the enterprise world. As you can see, I think it resonates a lot with what Max said. Things are becoming much more real time, and I think you'll see this across many industries in the next few years. The final bit I want to talk about is the control plane for running this kind of service. And I couldn't give a talk here without mentioning that we're also starting to use TiDB for the Databricks control plane, and it's a very exciting technology for that. So the Databricks control plane is all our infrastructure that runs the customer workloads, keeps them going even when cloud machines fail, when there are storage problems, when various things go wrong. So that itself is thousands of nodes across more than 100 regions, because we operate in the three major clouds here, Amazon, Azure, and Google, and they each have many regions, and we need to deploy our services in each of them. So we have many instances of this control plane that together manage these millions of worker VMs. And it's really important for it to be highly available and scalable, because people are building production applications. As you saw, 1/6 of the jobs are actually streaming jobs. So we can't go down when running these applications. So how did we start out building this? When we started out, we just built stateless Kubernetes services, and we used MySQL as the main database, and we used the version provided by each cloud, because we thought, hey, this is just a control plane. It's not going to need super high volumes of data, right? How many customers could we have? How many jobs could they have, right? It can't be that many. So that's what we started with. But over time, we saw that actually all these things are going. Customers come in, they set up a production job, they set up 100 production jobs, they set up 1,000, they start running automated queries that each submit a job, so you get a lot of them. Same thing with users, you go from a few expert data engineering users to maybe everyone in the company wants to connect and create notebooks, power dashboards, and so on. So we're actually starting to hit the limits of MySQL scalability in some of the largest cloud regions, and we have individual customers who want to run even more stuff. And we also ran into problems with the availability of it, especially for these real-time applications. It's not easy to maintain even single-node MySQL to deal with all the software updates, to fix it when things go wrong, and to do all that while avoiding downtime. So we started to look at TiDB for our next generation control plane, and we chose it as kind of the system to go on. And there were a bunch of attractive properties we liked. Obviously, coming from MySQL, we really liked the compatibility because we could migrate to it. But another subtle aspect that maybe people don't think about is when you're holding out something like this, you always want to be able to hold back. So we wanted a technology where, if something's going wrong, we can switch back to our old MySQL system. And it's really important to have the compatibility work both ways. So writing one query and being able to swap back and forth is really nice. Horizontal scaling, of course, very important. Zero downtime, you can upgrade the system, all without bringing anything down. And also, HTAP was really interesting to us because as people run these workloads, they want to analyze what they're doing on Databricks in real time. So, which jobs are running, when are they failing? If you're running many of these, it's really important to do that in real time. And without this, we would need to take many minutes at least to deliver that data to them and to write a lot of complicated logic for that. So experience so far, we're still in the process of adopting it, but so far things are working well. We actually prototyped one of our senior engineers basically took all our services and got all of Databricks running on TiDB in about 2 months. So we had to change a few things, a few queries, but overall, that's not too much work for one person to do. And of course, to roll it out in the real system takes longer, and we want to be cautious with it. But we've been, we're starting to do that too. And we found that the MySQL compatibility has been super nice for that because I said we can easily move even individual customers between MySQL and TiDB and move them back when things are going wrong. So all the infrastructure we had for moving things between MySQL databases also works for moving them between MySQL and TiDB. And we're also starting to design a bunch of features that are only possible with HTAP, like real-time reporting on what's happening in your system. And of course, we're super excited that TiDB supports Spark. We see many customers who are running online stores of various kinds, including TiDB, and who want to connect to them from Databricks and to push stuff back. So that's super cool to see. And I think that's only possible with open source technologies. So the ecosystem just builds around them and kind of maintains these integrations. So that's what I wanted to talk about. So overall, I do think the entire enterprise world is moving towards real-time data. At the slower end of the spectrum, things like data warehouses and data lakes that used to take months to get in your data and let you query it are starting to let you do that much faster using approaches like the lakehouse. And at the faster end of the spectrum, even the online systems are getting a lot more data in them and are trying to do more and more sophisticated analytics in real time. And it's really cool that these technologies many of them are happening in open source and they can work so well together. So thanks a lot.